Okay, so yesterday in class, one of the other sheets I gave you out was this sheet called Free Falling Objects. And it's just talking about objects that we drop. And so whenever you see an object falls freely or an object is dropped, there's a few understood givens that are there. If you drop an object, then it means the VI is going to be 0. Not if you throw it, but if it says an object is dropped or an object falls from rest or whatever, then the VI is going to be 0. Okay? The other thing is that why is it falling? Well, it's falling because gravity is pulling it down. And as long as we're at or near the surface of the Earth, then the acceleration due to gravity is 9.81 meters per second squared. Because it's special, we sometimes call it little g instead of an a, but it's an acceleration. So in kinematics, whenever it says it's falling, then you can assume that the acceleration is 9.81 meters per second squared, and it's always, 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 always down. You never have to wonder about which way is gravity going to pull me today if I step off my bed when you get up in the morning. Okay? So in a question then, they won't necessarily tell you these things. They'll just say it. So if you look at your sheet, a body falling freely from rest near the surface of the Earth accelerates due to gravity at a rate of 9.81 meters per second squared. So this value is what one uses for A. So if a question states an object is falling or dropped, then it's if it states it's falling or dropped, it's understood VI is 0. Now, what I didn't say there is if you actually throw an object upward, the VI won't be 0. You'll be giving it some VI. Let's say like maybe you're really strong, 10 meters per second, and that'll be up. But gravity will still be acting on it, trying to pull it down at a rate of 9.81 meters per second squared. So when you have an object going up and gravity pulling down, now you have to look after positives, negatives. Because usually we call up positive, so now gravity will have to go in as a negative because that's acting against it. Okay, so let's take a look at example 1, which says find the distance traveled and the final speed of an object falling from rest for 10 seconds. So from rest, VI is 0. For 10 seconds, delta t is 10 seconds. And its gravity, so A is it's falling, so due to gravity, so A is 9.81 meters per second squared down. Now, because it's falling down, it's moving down, delta D will be down, we can just call down positive here, because there's no other direction involved. And the question wants to know, find the distance traveled, find your delta D, and the final speed, your VF. So first, what equation do I know with delta D that has a VI, an A, and a delta T in it? And it'll be our delta D is equal to VI delta T, 1/2 A delta T squared. And because it's falling from rest, this VI delta T term goes to 0. So it'll just be delta D is equal to 1/2 A is 9.81 meters per second squared, and time is 10 seconds. 10 seconds squared is 100. Half of 9.81 is 4.905. So you should get 490.5 meters per second squared times seconds squared will just give you meters. Okay, so that's for delta D. To find VF, you have a couple of choices. You could do VF squared equals VI squared plus 2A delta D. You could also do A is equal to VF minus VI over delta T. The advantage of VF squared is you don't have to rearrange. The disadvantage is you're going to use this delta D that you just found that you could have screwed up. So I would probably be more tempted to use A is equal to VF minus VI over delta T, just because these were all the givens. Okay, you got to rearrange though for VF. It's not going to be too tough because VI is 0. And so rearranging VF, A delta T. So VF is equal to A is 9.81 meters per second squared, and delta T is 10 seconds. So VF is 98.1 meters per second. Now, in both of these, they worked out to be positive, and I called down positive. That's why there's not a negative on my 9.81. So if we wanted to put our directions in here, it said distance, so it's not displacement. But if it had said displacement, it would be down, and if it had said velocity instead of speed, we would put it down there. Okay, let's take a look at example 2, because this time we throw the object up. So a ball is thrown up with a speed of 5 meters per second. So 5 meters per second up. A is going to be 9.81 meters per second squared down. Okay, how long will it rise? Well, it's going to go up until it's going to slow down, slow down, slow down, slow down, and somewhere up here it's going to stop. And so it says how long will it rise? You're looking for delta t in part A. So we have a VF, a VI, and an A, and we want a delta t. So for part A, we would use A is equal to VF minus VI over delta t. Rearrange for delta t, take it up, bring the A down, VF minus VI over A. VF is going to go to 0, so it's going to be 0 meters per second minus, and I'm going to call up positive, so I'm going to put my 5 meters per second in as a positive, and that means I need to put my 9.81 meters per second in as a negative. And so then it's going to be negative 5 divided by negative 9.81. The negatives are just going to cancel out, and you should get a time of 0.50968 seconds for part A. Part B says, what will be its maximum height? So now you're looking for delta D. Well, you have a VI, you have an A, and you have a VF, what you're given. If we ignore the time, just in case we screwed it up, I would go with VF squared is equal to VI squared plus 2A delta D. You could also use your delta D is equal to VI delta T plus 1/2 A delta T squared, as long as you didn't mess up your T. But since we were given these other three, I know they're right. And so I need to rearrange for delta D. So VF squared minus VI squared is equal to 2A delta D, and then divide by the 2A. So VF squared minus VI squared over 2A. So delta D is equal to, VF is 0, so that can just cancel. So minus brackets 5 meters per second, and it's going to get squared, over 2 times negative 9.81 meters per second squared. So 5 squared is 25, divided by 19.62, and the two negatives are going to disappear, and we're going to get a delta D of 1.2742 meters. And the two negatives don't disappear, they cancel each other out. All right? Number C, how long after it leaves your hand will it return? Well, the great thing about throwing an object up is as it goes up, it slows down, it slows down, it slows down, and it stops. And then it turns around and it comes back and it speeds up and it speeds up and it speeds up. And when it gets back to your hand, it's going to be going exactly the same speed that you threw it with, just in the opposite direction. So whatever time it took to go up, which is what we found in part A, so I could go back here and say this is really the time up, that's going to be exactly the same as the time it takes to go down. The world is symmetrical. And so find the total time. All you would have to do is double the time up. So 2 times delta TU. So delta T total should then equal, doubling it, 1.0, I probably shouldn't trust myself, 0.968, and I know I rounded that. 1.0, okay, I was going to be right. 1936 seconds will be the total time that it takes before it returns to your hand. What will it be its speed? When will its speed be 20 meters per second? And what will be its speed when it comes back to your hand?